Each row represents a route to a network or a subnet. Oops, subnet. Okay. So if we look here, I'll just note each arriving packet is matched against the destination subnet field in every row. All right, so the bottom line here is all of the rows in the router are put there being the route, sort of how you get to these various networks and subnets. When the packet comes in, should be packet, each arriving packet is going to be matched against the destination subnet field in every row. Okay, the router goes through the whole table. Okay. So the destination IP address is going to be masked and compared with the destination subnet. All right, so let's start. If we have a destination IP address that equals 172.30.23.6, okay, we need to go through every row on the table here. Okay, so we're going to start at row 1. We take 172.30.23.6 and we mask it with row 1's mask. Right? If I mask it here, 255.255.255.0, so that's this mask for row 1. The result is 172.30.23.0. And remember, right, this is a binary number. I'm just writing the digits because it's easy for us humans to look at it. Okay? So I mask it off and I get 172.30.23. I compare that to this number, 172.30.21. Is that a match? So on row 1, let me write that as a row 1, the destination subnet is 172.30.21.0. Is that a match? It is. Does that match?
No.
Come on, Peanut Gallery, help me out. This is not a match. All right? That was row 1. That was fun, right? Do you want to do it to row 2? Let's not do row 2. Let's do row, what was it, 23? Let's match it with row 5. Remember, the router is going to go row 1, row 2, row 3, row 4, row 5, and it's going to find a match. Then what's it going to do? Is it going to send it? No. It's going to go row 6, row 7, row 8, row 9, row 10. And we'll talk about what it does in a minute for that. Right? So if we do row 5, hopefully we can see my destination was so the destination IP on the packet was 172.30.23.6. The row 5 mask is a /24, which means 3 octets of 1s followed by zeros. The result here is 172.30.23.0. And if I look at the destination here, is that a match? So the row 5 destination is 172.30.23.0. Yes. Okay. What a match means now is we're going to store it for later. And we're going to keep going through the rest of the table. Okay? It's kind of dumb. In my notes it says, is row 8 a match? And the answer is no. Okay. I'm not going to make you guys do one. And we'll get to go home. We actually are going to probably get. Let's see what all we have. Oh, we have some good stuff still. Okay. All right, so we go here, match. Okay, note. Each packet is matched against all rows in the table. Put an exclamation mark. Make sure you remember that. So if you have 10,000 rows, how many comparisons are we going to do? On average. Just on average. 10,000. Because we go through the routing table the whole way. This is one of the first contrasts with switches, right? Remember with the switch, there was only going to be one match in the table. So as soon as you find the match, you're done. So on average, a switch is only going to go halfway through the table to find a match. A router, though, goes through the whole thing. The point here is there might be multiple matches, and the best has to be found. And we will talk about that in a minute. Well, right now. All right, so here's the rules. Rule number 1, if there's only one match, that one is the winner. Should we just say wins? Okay, that's kind of the duh rule. The second rule is if there's multiple matches, the longest match wins. All right. So if we look at our routing table, if we have a destination on our IP packet of 128.171.17.56, okay, which rows does it match? If we look back at our table, 128, 171, 1756. All right, I've got 6, I've got 8, and I've got 9. Okay. Now the thing we know already is which one is going to lose. 8 will lose. Y'all see that? Because 8 has a 16-bit match. You see that? This matches, I'll note here again, it matches 6, 8, and 9. So 6 mask with 24. 8 masks with 16. Remember, the mask is on the row, okay? We mask every row separately. And then this one matches 24, okay? What does that mean? 8 loses. And then we get to our next rule. If there's more, what is that one? When there's multiple matches of the same length, the metric breaks the tie. Okay? And I'll just note, by the way, so remember we're 128, 171. Let me just remember or note up here. For 6, 8, and 9, it throws out 8 because it assumes that longer match is going to be a longer distance. Okay? So this is like saying I have a shortcut, and either 6 or 9 would be considered sort of like shortcuts. Does that make sense? The short match is considered to be sort of a general, like city of Norfolk. And this would be like, I can get you right to that street. You see that? Here I would expect to go to a router that's going to go to these, but these would be a more direct route. So I'll just note here. So a longer match is assumed to be more direct. Okay? So, but if there are multiple matches here, and now we need to break the tie between 6, 8, and 9, or actually between 6 and 9. I'll do that up here. No, that's not going to work either. Yeah, that'll work. All right, so again, I'm at 128, 171, 1756. These both match, but we go to the metric column here. Normally in the metric column, the lowest value wins, because this is the number of hops. Okay? The lowest value wins. So we'll note that. If it's hops, the lowest value wins. You have an option, just so you know, to set this metric column to be speed, and in that case, the highest value would win. But most people do hops. Right, so why is that one going to win? Or which one is it that won? Oh, 6 won, because it was 2 hops. If we look back at our original diagram, this is going to get really complicated. If I want to get to 128, 171, 1756, is that where I'm going? In here. And I'm right here. It makes sense to go here, because it's closer. Do you see that? 1 hop, 2 hops, there. If I go this direction, it's now 1 hop, 2 hops, 3 hops, there. You guys see why that one wins? So this one wins because it's more direct. Nice and easy, right? We're all over this stuff. Come on. Dr. Haynes, you act like this was so complicated. And it's not. All right? There is one last rule. If hops less segments, okay? The default row always matches. Okay? Which is my default row? Can you guys see that on here? Is there a row here that always matches? Row 10 always matches, right? And you can see that. If you have a 0-bit subnet mask, that's all zeros, and 0 times 0 is 0. Everything matches that. It's also, what would we call it? If anything else matches at all, the default row is going to lose. So the default row is like the I don't know where this packet goes. Y'all following me here? So the router goes through its whole routing table and it gets to the bottom row, and it uses the bottom row, this default row, when it doesn't know what to do with the packet. I don't know where this goes. And notice it's going to pass it off to 172.30.21, It's going to pass it to the border router. The border router, by the way, will probably just pass it to the ISP router. And then somewhere along in the internet backbone, there's going to be a router that knows where it goes.
Is that top one not a border router?
This one would be internal because this is a WAN link here for us. Okay, this is internet. Okay, these two links are internet. So you all still remember, right? The WAN, our WAN stuff is still our network. Okay, the internet though, that's like Wild West kind of stuff. We don't even know what's out there. We have control over this stuff. So the WAN is still our network. So we note that. Right, default row always matches. It's also the shortest match. It's usually going to send to a border router or if it is the border router, it's going to send it to the ISP router. And so my router at my house, it just basically has 2 entries, maybe 3. It has the entry for my house's subnet. It has an entry for the Cox subnet that it's connected to, and then it has a default row that just passes everything to the Cox router it's connected to. Okay. There's not a lot special there. Border router or the ISP router. All right.